Thank you, Marcy, and welcome everyone to Disaster-Resistant Wood Frame Construction, Part 2, Wall and Floor Design. The material we're looking at today is copyrighted, and so any use of that would require permission from the American Wood Council. And as Marcy mentioned earlier, we are a registered provider with the AIA, and this program is registered with them as well. You've hopefully seen the course description, but we will be working through two documents today. One is what we call the WFCM workbook, and it's a design example looking at high wind, high snow, and high seismic loads and solving for those loads per the 2012 Wood Frame Construction Manual. And so hopefully you have those two documents. Brian's providing links to those. They're also in the new handouts part of your dashboard. So I'm going to close this screen and jump then to our website quickly, just so you can get a sense if you weren't able to get the handouts or been able to get to other portions of our website. I thought you'd be interested in seeing how to navigate from our homepage, awc.org, click on Codes and Standards, and then click on Publications, either here or here, which will take you to a publications page. And the 2012 Wood Frame Construction Manuals, the second row down here, you see all the various standards and versions of those standards here, one easy to find location. So you click on the 2012, it's going to take you to this WFCM page, and as you scroll down you can get a free view-only copy of the Wood Frame Construction Manual, and here you have options to buy a printable version of the PDF or a hard copy, and then the workbook is located below here as well. One last thing I'll point out on this page, and we've gotten this request from builders and others who only practice in one specific wind region. We've developed these documents called high wind guides that are specific to a certain wind speed and exposure. So you see here's 115 mile per hour exposure B. We've got exposure C here on the right. We go 120, 130, 140, 150, and 160. And so each of those guides are downloadable and printable if you're interested in something like that that's very specific to a certain wind region. That might be helpful for you as well. Again, we'll be working through this workbook and standard today. I've got them here on my screen like this. You may have printed out one of those documents like the workbook. Feel free to take notes along the way. I'm going to ask Marcy if she would come back and kick us off with two poll questions here to give us a sense of the audience and whether you were here for part one.
Absolutely. All right. So our first poll question, as always, is what is your profession? Are you an architect, builder, code official, other, or an engineer? So, and you can see I actually had to do these a little bit alphabetically. So, I'm going to give you about another 5 to 10 seconds. And actually 80% of you have already voted, and that's about it. So let me close, and I'll share. So about 80% of you are engineers, 12% code officials, and a smattering of architects and other people. So
Great. And what was that second poll question, Marcy?
All right. The second one is whether or not you've attended part one. So did you attend part 1 of this webinar series, STD 335, Disaster Resistant Wood Frame Construction, Loads and Roof Story Design? Did you attend it? Yes, no, or maybe some of you actually watched it online. So if you would go ahead. So. Again, I'm waiting for about 80% of you to vote. And there we go. All right, and then sharing it. So about 74% of you did watch or participated in the first part of the series. 21% did not, and about 5% watched the online version. All right.
Okay, great. That's really helpful. Gives me a sense of how to proceed today. So one of the first things I'll do here, just for those of you who weren't able to attend that first session, if you weren't, it's recorded and available on the website, to give you a sense of this document and how it's laid out. Last time we looked at the loads and worked through the roof story design. Today we'll look at second floor design and first floor design, mainly shear walls and diaphragms and connections around those. The loads that we're looking at for this structure are 160 mile per hour exposure B wind loads and seismic design category D1. We've got a ground snow load of about 30 pounds per square foot on the structure. And then our deflection limits down here near the bottom that we talked about especially for the walls today that we'll be looking at, an L over 180 or H over 180 is what we'll be using, assuming wood siding, and I'll talk a little bit more about that when we get further into the discussion. So I'm going to jump then to that second story, page 31 of the workbook, if you're following along. The other thing I want to do just quickly is give a quick overview of the wood frame construction manual and the table of contents there to give you a sense of how that document is laid out. And so the wood frame construction manual itself, the ANSI standard, up front defines sort of the general information, the scope of the standard, the material standards that are referenced, definitions, and symbols. Chapter 2 is what we call engineered design, and that's broken up into several parts. We've got general, connection design, floor systems, wall systems, and roof systems. And I think I mentioned this last time, but we, in the standard, sort of work from the foundation to roof, and that's the way the code's laid out. But in the design process, we work the opposite way, from roof down to the foundation, to make sure we can transfer loads and ensure our load path down to the foundation. So we kind of work backwards in the document, and so that's a little bit of a twist for how the standard is laid out versus how we work through the example. Chapter 3 is where we spend most of our time in the wood frame construction manual, and that's called prescriptive design. I will today, just to address some of the folks who were wondering why we focus so much on prescriptive design, talk a little bit about the underlying calculations in not only Chapter 3, but also in the engineered design in Chapter 2, and give you a sense of where that's coming from. And we realize that there's a lot of information covered here. We're thinking this is the best way we can think of to cover this particular topic, rather than me switching back and forth full screen between these documents. I've got them split out, so maybe a little bit hard to see, but hopefully if you want to follow along in one book or the other, again, this will be recorded and you can refer back to this as well. So let's jump into the workbook and get to the next page here, and we're going to start right away with wall framing. design. And you see when we start here, we've got the table references right here at the top, table 320A and B, and so I'm going to jump there in the standard and follow along with the bookmarks to get us there. Here's 320A, and I'll maximize that on the screen so you can see it. And then we'll start working through the example problem. So first thing I'll mention here is our deflection limit, L over 180. If I were to do this workbook over again, and we probably will update it for the 2015 version, I'll probably change this to L over 240. This is sort of a new set of tables in the 2012 wood frame construction manual where we've got various deflection options. And so for the wall system, the exterior wall system we were looking at with wood siding, L over 180 would work, but then I realized as we got into a little further into the example that we've got gypsum on the interior, so it would probably be better to bump this up to L over 240 since we've got gypsum on the interior. That will change your results, obviously, and so we'll, for today though, for this example, just look at L over 180 as the deflection limit. We've got 9-foot wall heights in this example, and that's all covered in the intro to the workbook, so you'll have to trust me when I say that that's what we're looking at. And then we've got a roof ceiling and one floor above, and I'll point out the little icon here in the top right of the workbook. If you can see my cursor here on the workbook, this will give you a sense of where we are in the structure. So it's a 3-story structure, and this particular floor of the structure has a series of bedrooms on the right-hand side that's shown in this gray box. And over here on the left-hand side is a master bedroom with a vaulted ceiling. And so we'll be looking at 2 different designs accounting for 9-foot walls and a normal flat ceiling in one, and then vaulted ceiling in this left-hand side. So we're carrying a roof ceiling in one floor above these wall studs, and the sheathing on the exterior is wood structural panel sheathing. So because of that, and to make sure we're on the right page of the workbook, I'm going to jump back over here to the wood frame construction manual. So again, we've tried to make it obvious here in the header of the tables. We're looking at exposure B wind loads, and H over 180 is our deflection limit. But I want to point out here that this assumes minimum sheathing material. And what we mean by minimum sheathing material is gypsum, not necessarily wood structural panels. And that has to do with the system factors that we use for stud design. So I'm going to actually jump back to the table of contents, and we're going to scroll down to table 320B1, and I want to show you the difference between A1 and B1. B1 tables assume 3/8 inch wood structural panels on the exterior of the wall system. The other thing I want to do is make sure we get to the right wind speed. So this is 140 max on this page. The next page down, on page 243 of the wood frame construction manual, if you've got that open or on your desk or following along, actually has 160 mile per hour wind speeds. Okay, so that's how basically the document is organized. Let me talk a little bit about those system factors. So in the wind and seismic standard, that's one of the reference standards underlying the wood frame construction manual, we've actually incorporated system factors for calculating bending capacity of wall studs. And those system factors build on what is also a system factor in the NDS called the repetitive member factor, C sub R. On the NDS, that C sub R factor only goes up to a maximum allowable increase of 15%, so a factor of 1.15. In the wind and seismic standard, knowing that we'll have gypsum on the interior and wood structural panels on the exterior, we've allowed that system factor to go as high as 1.5 for 2x4 wood studs. So if it's sheathed with wood structural panels on the outside, which this is, and gypsum on the inside, we are actually increasing the bending capacity for those studs as much as 50% for 2x4s. I think it's something like 30 or 40% for 2x6s and 20% for 2x8s. It ramps down to about that same 1.15 for 2x12s, but we're not designing 2x12s in the wall system here. So just wanted to point out that's why we showed different headers in these tables. These assume that increased system factor. The other thing that I want to show you that underlies these tables before we jump in and start, and hopefully this will give some of you designers a little bit more comfort level in what we have here. And I've got a version of the commentary up on the screen now. If you want the commentary, you actually have to purchase the document. Now, we do make the standard available to download, but we don't make the commentary free to download. And so I'm going to get to the commentary because that provides the background calculations for each one of these tables. And so you're seeing here, I'm going to show the commentary for 320 A1 to A6. That's the minimum sheathing material, but there are background tables for B1 to B6 as well. But the analysis is an iterative analysis for these stud tables, and so we're looking at determining the stud length based on the effective wind area using component and cladding wind loads. And I want to talk a little bit about that as well because there's often question about using component and cladding wind loads versus main wind force resisting system wind loads. And to just make it as brief as possible because we've got a lot of ground to cover here today, there are two approaches to calculating stud length in a wall system. And the interpretation we've gotten from the ASCE 7 Wind Loads Committee is that we are going to check stud length based on component and cladding loads alone. And the second check that you can do as a designer is to check combined bending and axial loads using main wind force loads on the structure. So we do not combine axial and bending using components and cladding loads. We do a combined bending and axial check using main wind force loads. And there's a paper on our website, and I ask some of the folks that are helping out here to put that link as well for you to download if you'd like. It's called Considerations in Wind Design of Wood Structures. It's on the free downloads page of our website, and somebody will get that link to you while I'm talking here. But that, again, allows us to look solely at the bending loads on these studs, and those control over the combined bending and axial using main wind force loads for the scope of studs that we're designing in this wood frame construction manual. So that's an often overlooked assumption or interpretation, and I'll leave you to looking further into that on your own to verify. But those are the assumptions underlying the stud analysis here. And so, as you can see here in the commentary, we go through the analysis determining all the wind loads from ASCE 7. We've done all that for you. We've done the stud check and check deflection and bending to come up with the final result that shows up in this table. So now back to our workbook. So again, it's an iterative approach. We could try 2x4s here, and what you're seeing in this table in the workbook is that 2x4s actually work for the 9-foot studs that we've got. Let me take you just quickly to the footnotes in this table so that you can see that we also, oh, I'm sorry, I'm in the wrong footnotes. Let me take you to footnotes to table B. And so the other point that we'll make is that the table 320C that's shown here is the maximum length that studs can be based on the axial loads, and those come right out of the IRC. So there's two checks that we look at. We look at in the workbook a maximum wind load check, and then we look at a maximum length based on dead and live loads, and those dead and live load limits are based on this table here in the table 320C in the workbook, and those come right out of the IRC. And so the 2x4s in this particular case would work, but the other footnote that I want to point out is up here in footnote A, and that has to do with end zone loading requirements. And if you have, or obviously we're going to have studs in the end zone, and what happens in that end zone is that the loads are higher. And so there's this adjustment factor of 0.8 on the spacing of the studs within those end zones. And so we know that if you're spacing studs at 16 inches on center in the wall system, you're probably not going to get to that end zone, which is the last 4 feet of the walls typically, and then drop those down to 12 inches on center. You're going to want to keep a consistent spacing along the wall. So we've got a couple of options here that you can see with this table. We could use number 3 and stud 2x4s, and then at the corners space those at 12 inches on center because of that adjustment. Or we could design for a higher grade 2x6 stud at 24 inches on center, and then because of that adjustment factor back off to 16 inches on center. And so that's what we're using as a solution here. So in the table for Doug Fir Larch, for example, number 3 and stud grade 2x6 will work in those lookup tables. It gives a maximum length of 11'6", but then that maximum length for axial loads is 10 feet based on the live and dead load from table 320C. And so we're going to use that 16-inch on center spacing to satisfy those requirements. And the yellow here just indicates, if you looked at the key, that that's what will work for this particular example. So that's our, let's see, those are our load-bearing studs. That covers the load-bearing studs with roof, ceiling, and one floor. Then we'll go to the other end of the building. So on page 33 of the workbook, we'll look at the gable end walls, the non-load-bearing studs. And we've got a couple of options here as well to look at. And what we're looking at here is actually, because we've got a vaulted ceiling here on this end of the structure, we've got 2 options. One would be to balloon frame all the way to the peak and we actually looked at that in the roof design example last week. Or what we ended up resolving last week in the roof example is this little triangular peak here. We're just going to frame that in. We've designed 6-foot studs there. So we're going to design these 9-foot plus 3-foot studs here. So we've got 12-foot studs that come up to that vaulted ceiling location. So then we're going to design a 12-foot stud, and again, we've got wood structural panels on the outside. And again, going back to our table here in the wood frame construction manual for 160 mile per hour wind loads, and we know we're going to be looking at 2x6s, and we're going to drop down here and see if 24 inches on center actually works. Let's just design the Douglas fir larch studs first, and we'll come across here, and for a 2x6, let's see, 24 inches on center. Now, hang on just a second. I'm not picking up why I'm not showing the same maximum length there, 15'2". Give me 1 second to get my bearings here. Oh, we're in exposure C. That'll get you every time. There you go. So there you see the mistake that I made. I was in the exposure C table. So I'm going to back up here to the correct table, which is exposure B. I apologize for that. I need to get back up here to table B1. So I was way too far down in the tables there because I was too close to the footnotes. So I know I'm messing you up. I'm going to give you a chance to catch up with me here in just a second, so as I get to the right table, and this is probably important for you to see that. Make sure we're navigating these tables properly. So I'm in the exposure B table, H over 180, 3/8 inch wood structural panels. This is table 320B1 on page 243, and we're under the 160 mile per hour wind zone. We're going to look at 2x6s, and I'm going to scroll down here, and we're going to see that that matches up with that 15'2" span that we see in the workbook. So sorry, I kind of stumbled through that when I skipped up from the footnotes, but this is the span or the height of the table value that we see here in the workbook. And then again, because of footnote A, we're going to end up reducing that spacing down to 16 inches on center. So that meets all the criteria of those tables and allows us to balloon frame this stud up to that 12-foot wall height. So I'm going to jump then to the next page, and that's the other end of the building where we've actually got a 9-foot wall height. Won't run through that example since we've done one already, but we end up using 2x6s as well on that end of the building. And that's going to become a recurrent theme throughout the structure where we're using 2x6s to handle these wind loads, these 160 mile per hour wind loads on the structure. 2x4s don't end up working everywhere, and so that's what we'll be reusing. The next part of our analysis is to look at the top plates in the structure. And so for a building that is receiving wind loads, that building is going to act much like a large deep beam. And because it's acting like a deep beam, the tension cords, if you will, for that deep beam are the top plates. And so there's going to be a fairly substantial tension load on those top plates. And we're going to go to table 3.21. So I'm going to jump here to the bookmarks and scroll down to table 321 of the WFCM. And if you're following along in your workbook, we're going to go here, and this covers both exposures B and C. And the building dimension we're going to look at first is the 32-foot building dimension. And we see that to handle that tension load in the top plate, we need 13 16-penny nails on each side of the splice. And so we come back over here to our workbook, and we see we've got the 13 16D nails. And if we're going to space those, two of those every 6 inches on center, then we're going to end up with about 4 nails per foot, and so that's going to require about 3.5 feet. The 40-foot dimension is going to require a few more nails per that table, so that's going to require 16 nails, and we're going to need about 4 feet of splice length to get those 4 nails in. So that's a real quick, again, there are a lot of calculations behind this table, but you can see how easy it is then and time saving. And that's the other thing I didn't address. You know, with residential construction especially, your margins are going to be pretty tight as an engineer, designer, and so this we feel like is a pretty handy tool to help you through that design process. It also gives you a lot of great examples if you're looking through the commentary to understand the analysis that is behind each of these tables. And so if you want to fine-tune the design, you're certainly able to do that, and you have an example to work along with to fine-tune the design. So I'm going to stop there. I'm going to ask Marcy to come back and give us our next poll question.
Absolutely. WFCM has tables for exterior studs with deflection limits equal to H over 180, H over 240, H over 360, or all of the above. All right, about 10 more seconds. All right, and we're going to share it. So about 77% say all of the above, 19% say H over 180, or 2% just a smattering for the other two. So.
Okay. Thanks, Marcy. And for those of you who guessed H over 180, I probably wasn't as clear as I should have been. That's the example problem we're looking at. Let me jump down here to table B2, which has the H over 240 deflection limits, and then table B3 has the H over 360. I probably flew past those in the example, and so you didn't see those. But just so you know, that allows you to determine your stud lengths for these tighter deflection limits. So if you've got other types of siding, veneers, or other brittle finishes, then these H over 360 limits will help in those areas as well. So let me get back to the workbook, and we'll move on. Yes, go ahead.
I have a question that came in.
Great.
That perhaps you can answer, and it has to do with someone mentioned that in their part of the country, reduced stud spacing at the end zone is rarely used. Are there any tables that incorporate the 0.8 reduction factor?
Yeah, so I probably kind of glossed over it a little too quickly, but that 0.8 should actually be worked into your design ahead of time. And so here in the workbook on page 34, I've actually solved the example using a 24-inch on-center spacing, knowing that that 0.8 factor is required. And so that backs it down to 16 inches on center. So whether your part of the country realizes it or not, that is an ASCE 7 provision. Those end zones do have higher wind loads, and so again, and if when we redo these tables, I guess we could do the most conservative approach and incorporate that 0.8 factor from the beginning. and then allow you to back that out. But that is a nuance to these tables that you should be aware of and be prepared to address in the design or analysis that you're doing. So, thanks, Michelle, for that question.
Mm-hmm.
I'm going to jump to header design now, and so we're on page 35 of the workbook, and we've got a 32-foot building width, and so I'm going to now also in the wood frame construction manual jump to table 322, and I'm going to go ahead and jump to 322B1 because that's where we end up for this example. And so I'm going to go there, and we'll talk about why we're there in just a second. So our building width is 32 feet. Our header, the largest header in this wall, is 6 feet. We've got a 30 pound per square foot snow load and a 160 mile per hour wind load. You might say, well, why does a wind load make any difference? Well, we now are going to need to check the wind load. Since it's such a large wind load, we're going to check the lateral wind load on these headers to make sure that they're okay in bending laterally. So let's talk, though, before we get there, about dropped versus raised headers. So you see in the workbook and in the wood frame construction manual, we've got dropped headers and we've got raised headers. So a dropped header is right down over top of the window or door with cripple studs above it. The raised header is typically right up under the top plate, and the top plate is nailed off to the top of the header to provide full lateral support. And that's been an issue that we've heard about over the past few years, and one of the changes to this wood frame construction manual, if you are familiar with earlier versions, is that we now tabulate both dropped and raised headers. For the dropped headers, we're going to assume a lateral stability check. So we're going to do a lateral buckling check on the headers. The raised headers will assume full lateral support because those are braced off by the top plates in the wall system. And so if we go to the lookup tables here and note that we're looking at dropped headers in the exterior load-bearing walls, 30 pound per square foot snow load. We end up having to interpolate between 24 and 36 feet because our building width is 32 feet. And we're going to drop down here to 3 2x12s, and we see that that'll span somewhere between 6 and 6'9". And so because we have to interpolate, this one up above for 3 2x10s at 5'7" won't quite make it. And so that's why we're ended up with 3 2x12s for this particular example. And that's carrying that roof ceiling and one center bearing floor. So if we were to look at the raised headers, those then are in table 322B2, and you see it says raised here at the top. Those again assume full lateral support at the top, and we drop down here to 2 2x12s, and that will actually work with 2 2x12s instead of 3 2x12s. So if we use a raised header in our example problem, we can get by with a little bit smaller header sizes. So that's one thing to be aware of. Then the next place we'll go is table 322F, and we'll scroll down here and take a look at our jack stud requirements. So now we've got to make sure that we've got enough bearing capacity underneath of each of the headers to carry those loads down through the structures. And so again, with a 30 pound per square foot ground snow load, and in this case, if we're looking at, well, let's see, are we doing the 3 or the 2 ply system? So for a 2 ply system, you'd look here at the 3-inch because of the bearing width. For the 3 ply system, we'd look here, and so we drop down to our header span of 6 feet. And so if we're 2x system, it's 3. If we're in the 3x system, it's 2. So I think we went with 3 here in the jack studs to be a little more conservative in case you decided to use the 3. Also notice that there's a roof span adjustment factor there in the footnotes. So we do have that adjustment here in the footnotes. So always look at the footnotes, figure out what those adjustments are, because we've got 9-foot wall heights, I'm sorry, because we've got a 32-foot roof span system. To make it easier to tabulate, we will use that adjustment. But it doesn't bring us down below requiring 3 jack studs in this system. So if we were to choose dropped headers, so because the raised headers are right up underneath the top plates, those will have full lateral support. If we use dropped headers, then we're also going to have to check the wind loads on those studs. And so we go to table 323A for that one. And let's jump here, and we're exposure B, and those are the dropped headers. And we're 160 mile per hour exposure C, and so I think we've figured out that dropped headers required 3 2x12s, and so let's just look down at 3 2x12s to see what the wind load span is for those. So if we're looking at 160 mile per hour wind load, exposure B laterally on a 6-foot header, it works because we can actually span 9 feet. But it is interesting to note that you are still going to have a limit, a span limit, based on those lateral wind loads on the wall. So we could actually get by with about a 2 2x8s for this 6-foot header in this particular example. But because we've got gravity control, we're gonna go with the 3 2x12s. Then the other thing we'll look at are the number of king studs that are required, and for that we go to 322 or 323C. So I'm going to jump down to 323C, and these are king studs or full height studs. These apply to both exposure B and exposure C. Our wall stud spacing is 16 inches on center because that's what we tried to design for. Our header span in this case is 6 feet, and so we see that is going to require 3 full height studs on either side of the header, and that's because we've removed a few studs in that 6-foot span. There is a table 323D you can look at on your own for you engineers or those of you who want to fine-tune those full height studs more. This table 323C assumes that the maximum bending load is at the center of the stud. We know for where those headers are going to be located, it's not always going to be at the worst case center of the stud. So this table 323D allows you to resize or reduce those king studs or full height studs based on where that maximum load will actually occur in the stud. So you can take a look at that on your own. Back to the workbook over here on the left. We've solved for the 4-foot and 3-foot headers as well down here at the bottom, and so you see that those are already done. I'll point out this note here at the bottom in red that per WFCM 34143, a lot of those jack studs could be replaced with an equivalent number of full height studs if you use gravity connections to attach the headers to the full height studs instead of using jack studs. So there's an exception there as well. For our exterior non-load bearing walls, we're on page 36 of the workbook. and for window sill plates. And so we're going to design a 6-foot window sill plate. We're going to go to table 323B, so back over here in the wood frame construction manual. Again, make sure we're in exposure B tables. And these are non-load bearing walls and sill plate. So we're looking to design the sill plate for 160 miles per hour. We see that we need a 6-foot sill plate. That won't actually work. That only 2x4 only spans 5 feet. So we are going to have to go to a 2x6, which is good because we've got 2x6 walls. That'll span 7'3", and so that works for this example as well. And so here's the 7'3" span. There is a wall height adjustment footnote that you need to be aware of, but that actually allows us to increase the span to 7'8" instead of decrease it in this particular case, because we assume 10-foot wall heights, and we've got 9-foot wall heights. So that's something else that you need to make sure you're always looking at the footnotes to the tables. For interior load-bearing headers, won't spend a lot of time on that. Those are in table 324, A through C. Those lookup tables are very straightforward, similar to what we've looked at here already. And then for interior non-load-bearing headers, the IRC allows you to use a single flat 2x4 up to an 8-foot span. And so that's a prescriptive limit there that we'll see. So I'm going to just stop there real quick, take a look at my notes, make sure that I'm not due up for any poll questions before we jump into shear wall design. And I really want to get into shear wall design because this is one of the more intense examples in the workbook. So I'm on the workbook page 37, and we're going to start taking a look at our walls. You see the icons here in the top right. We're going to look at our load-bearing and non-load-bearing walls. One of the first things we do is look at table 313A and B, and we'll go there in the wood frame construction manual quickly. Sorry, there's no other easier way to get there, but if you turn to page 197 of your wood frame construction manual for exposure B, 160 mile per hour wind loads and studs spaced at 16 inches on center, you see that that requires wall cladding of 15-30 seconds just to handle the suction loads on the structure. So I did that just because we want to make sure we're looking at those in both directions. So the suction loads are actually going to require a minimum 15-30 seconds on this particular system. So before we even get to shear wall design, we see a minimum thickness of 15-30 seconds wood structural panels. These are the wall details. They come from the front end of our book. We're probably just going to look at the north elevation wall for this next example. I'm going to point out that it's got 24 feet of full height sheathing, and that's in between these window and door openings. So we've got 3 feet here at each end, 3 feet between each of the windows, and then 6 feet between the windows and this master bathroom window here in the center. So keep that in mind as we jump to page 38 of our example problem. And I'll point out along the way too that each of these examples shows a location in the wood frame construction manual. In this case 3.4.4.2, and that gives the sort of chapter and verse, the enabling language for this design. It references these tables, 317A through D. And so I'm going to jump to 317A real quick in the wood frame construction manual. So make sure we're starting in the right place. Um, and we've got, again, a wall height of 9 feet. Number of stories braced is showing up as 1 because we're on the 2nd floor. So one quick note here for seismic design. In section 3.1.3.1 that's referenced here, if we had a full attic all the way across this building, that would actually be treated as a second or an additional story. In this particular case, we've got a partial attic, and so instead of doing a conservative approach and assuming an additional story, what we can do when we get to the seismic design is increase our dead loads. And so we're going to assume 1 story instead of 2, and then we're going to increase our dead loads per some of the footnotes. And so we'll point those out when we get there. For our wind loads, again, we're at 160 miles per hour, and the aspect ratio is 3.5 to 1, which means for our 9-foot walls we can go 2.6 feet for wind. For seismic, the aspect ratio is 2 to 1, which means a minimum 4.5 feet of wall panel or wall segment. And so keep that in mind because we'll look at some footnotes that will help us work around some of those. Our sort of baseline wall that is part of the assumptions in the wood frame construction manual is that we've got 8-penny common nails on the exterior at 6 inches on center around the perimeter of these panels, and then in the field they're 12 inches on center. We're assuming a minimum 3/8 inch wood structural panels over all the framing members. On the interior then we've got gypsum, 1/2 inch gypsum is the assumption on the interior, and we've got 5-penny cooler nails, and those are spaced at 7 inches on center around the perimeter, and then 10 inches on center at the center of the document. So when we jump to page 39 of the workbook, we'll do the seismic design first. So that's up here at the top of the table. You see seismic first. Again, we're just going to look at one wall, which is 2-2. That's that north wall. It's got a 9-foot height and a length of 40 feet that we're looking at first. These are our load-bearing walls. And then that length of full height sheathing that we talked about earlier is 24 feet. So here we see that we actually need to jump to table 317C1. So I'm going to jump down to the seismic design section. This is 317A, and here's 317C1, and we see that's for a ground snow load of 30. So again, we're doing the analysis for you in these tables that are going to save you a lot of time, hopefully, in the design process. So we're doing seismic analysis with that ground snow load assumption of 30. We also tabulate 50 and 70 pound per square foot ground snow loads here. Our seismic design category is D1, which is down here in the bottom center of this table. Our length to width ratio is 1.25 in the workbook. So again, we end up having to interpolate here in the tables between 1 and 1.5, but with that roof and ceiling, we come down here to a building dimension of 40 feet, let's see, length or width minimum, W. So we're looking at W, which is 32 feet here. So this is W of 32 feet. So that's right here. We come across and we see that L that we're trying to calculate the full height sheathing required, we interpolate between 7.3 and 10.2. And that ends up being 8.8 in the table here in the workbook. So that tells you the length of full height sheathing that you need in this particular wall system. Now there are footnotes in the table as well, so let's jump to footnotes 2 and 4 because those are showing up here. And so we'll drop down here to footnote 2, and what that tells us is on page 217 of the wood frame construction manual that for 2-story above grade, we can actually multiply those wall lengths by 0.92. So we're simplifying the analysis, assuming a worst case 3 stories, but you can back that down based on a 2-story building, which we're looking at here. Here in footnote 4, there's a big table, and I mentioned that our attic system doesn't stretch across the entire system. So I'm just going to go straight to our assumption here is a roof ceiling assembly dead load of 25 pounds per square foot. Again, you can look at that on your own. There's some engineering judgment assumed here in choosing those increased dead loads for that additional roof ceiling assembly because of the attic. But that 1.24 factor is what we're assuming as an increase. But again, if you were to assume a whole additional story up there, your wall length requirements that you pull out of the table here, instead of 8.8, it's probably going to be twice that. It's probably going to be 16 feet required. We're going to end up bumping it up by about a 50% increase. So let's then take a look at one more adjustment factor. So I'm going to jump now to table 317D, and if you're following along in your wood frame construction manual, I'm on page 218. So I'm going to spend some time talking about table 317D and its purpose in the wood frame construction manual and how helpful I think it'll be for you. The first thing I want you to do is scroll to the bottom of the table and take a look at the gray bar that near the bottom. It has 3/8 inch, 7/16, 15/32. It has 8 penny common nails at 16 inches on center. The studs spacing is 16 inches on center. And so I talked about our baseline earlier. This is the baseline wall configuration in the wood frame construction manual. So I'm getting you our baseline, and I'm going to have you circle here in a second a couple of numbers. So this is 1/2 inch gypsum on the interior. So what's in the gray is your exterior wall. What's down here below then is what's on the interior of your wall. So if you had no sheathing or no non-rated sheathing on the interior, that would be this line. We've got 1/2 inch gypsum, and again, this is our assumption for the wood frame construction manuals, that 1/2 inch gypsum. You see here we're showing the wind load capacity, the seismic load capacity, the aspect ratio limits, and then this is your adjustment factor that I want you to circle. These are both 1 because this is our baseline. And so this is where you start. You can circle this whole block down here if you want to, but these are your adjustment factors. And this is how you then could go to a tighter nail spacing to increase the capacity of your wall and therefore increase the length of your wall. And so we're going to I wanted you to see that because we're going to take a look at one more adjustment factor to this table, and that's the aspect ratio adjustment factor. Again, it can be a little bit complex, but we're trying to provide as much flexibility for you in the design process as we can. If we had met the 2-to-1 aspect ratio for these shear walls, we could have avoided this additional complication that we've got here, but we can't, unfortunately. And so what we're looking at here with footnote 4 is that if we exceed that 2-to-1 aspect ratio for seismic, we can go all the way up to a maximum of 3.5 to 1, provided that we take the adjustment that's in the wind and seismic standard, table 4.3.4. And I'm not going to jump there because it'll take too much time to go there. But if you were to go there, you'd see that there's an adjustment factor. And I'll come back here to the workbook now and take a look at this first footnote in the workbook that I've highlighted here below, because that gives you the explanation. If you were to go to table 4.3.4 it allows you to take a 2B/H adjustment to your capacity. Well, since we're dealing with shear wall lengths in this table, we're using the capacities that are spelled out in the table to calculate a shear wall length. Then we're going to have to take the inverse of that adjustment factor. So that 0.67 is what it ends up being, with 2B/H ends up giving us an adjustment factor of 1.5. And that's the factor that shows up here. So that's allowing us to increase it's requiring us, not allowing us, but it's requiring us to increase the length of our shear wall required because of the capacity reduction, because we don't meet the aspect ratios of 2 to 1 that are required for seismic design. So now I'm going to take this 8'8" or 8.8 foot length that was tabulated. I'm going to adjust by these additional factors that we've now worked through in the tables, and that comes up with a 17.2 foot requirement for length of shear wall. We've got 24 foot of shear wall, and so we've got plenty to meet that particular requirement. So you know, again, a little more complicated because we don't meet the 3.5 to 1 aspect ratio, but it does give you a way to resolve and come up with a solution. So I'm going to jump now to the wind load criteria, wind load design for this particular example. And we're going to jump back to table 317A, which is one of our lookup tables. And I'm just going to use the navigation tools here to get back up to 317A. We need to get to page 211 of the wood frame construction manual. Make sure we're in exposure B. Make sure we're under the 160 mile per hour column. And looking at the roof and ceiling requirements, our building dimension that we're going to look at first is the 32 foot dimension. We're going to work our way across here and see that that requires 10.3 feet of shear wall. And sure enough, here in the workbook, we see that that requires 10.3 feet. There is no sheathing type adjustment because that is going to end up being enough shear wall. We've got enough shear wall. We've got 24 feet, so we've got plenty. So we're not going to have to reduce our nail spacing at all. We'll do that on the first floor, and you'll see how that works. Our roof height adjustment factor, again, we looked at that, something similar to that earlier with seismic, but let's take a look at the footnotes to these tables on page 213. Again, to simplify the analysis, we assume a certain mean roof height in doing the wind load analysis. So footnote 4 here says that we're assuming a 10-foot wall and a 10-foot top plate to ridge height. And so that gives you a certain area depending on the slope of the roof. And in our case, we're at 7 and 12 for the roof, so we're going to be above 6 and 12. We're at about a 9-foot mean roof height, and so if we were to scroll across between 5 and 10, we end up interpolating here for this particular example, and we come up with an adjustment factor of 0.92. So we're going to be somewhere in that 0.92 range. It actually ends up being somewhere between here and here. So that then again allows you to increase your allowable or your required wall length. Or actually, sorry, that's a decrease in your allowable wall length. And again, we've got 24 feet, which is plenty, and so this ends up being okay. So that is a segmented shear wall design example. Before I jump to perforated shear walls, I want to just kind of give you a sense of the difference between the perforated and shear and segmented approach. So to do that, I'm actually going to jump to the wall detailing summary. So in your workbook, I'm going to jump to page 49. So if you're following along your workbook, jump to page 49. The reason I'm doing this is to give you this is the quickest way to get to a picture that shows the difference between the segmented approach and the perforated approach. So this is the wall that we just designed, the 2-2 north elevation wall. And I think seismic ended up controlling in this particular example, so it requires a little over 17 feet of wall, full height walls. And so we've got 3 and 6 here's 9, that's 18. So you see the hold downs around each one of these wall segments. Well, for the segmented approach, you would be required to put a hold down at each one of these locations. So that ends up being 2, 4, 6, 8 hold downs. What the perforated shear wall approach allows us to do is sheathe this entire wall system and stiffen it up. We might need it to decrease our nail spacing or go to a thicker sheathing. We'll see in a little bit. But in exchange for doing that, we can move our hold downs out here to the corners. And so that's what you're seeing here with the perforated approach, is a fully sheathed wall, fully sheathed wood structural panel wall, but we're able to move our hold downs to the corners. So that's what I wanted to show you before we actually jump to the perforated shear wall approach. What are we trying to accomplish now? So what we're trying to accomplish back on page 40 with the perforated shear wall approach is we're going to take that segmented approach that we just did, and we're going to use those increase or decrease potentially, we'll increase the stiffness of the wall and allow us to move the hold downs to the corners. So that's what this exercise here in the table is about. So we're going to again look at the 2-2 wall. The maximum unrestrained opening height in this wall is 6 feet. That's that large window, bathroom window in the center of the wall. And so that gives us 2h/3. And I'm going to jump then to table 317E. And I'll just jump this way. That's about the easiest way to go in the wood frame construction manual. So on page 222, we see we have a perforated shear wall full height sheathing adjustment table. And we said our maximum unrestrained opening is 2h/3. So on a 9-foot wall, that's a 6-foot opening. So we need one more piece of information, and that's the percent of full height sheathing on that segmented shear wall. So what we calculated earlier is a minimum length of full height sheathing for seismic. And I'm going to jump back to that table. It was 17.2. It's in the table just above. It's this number right here. So that's what's calculated for the segmented method, 17.2. We're plugging that in here to this particular cell to show that that's the minimum length calculated per that segmented approach. And then we're going to divide by the length of wall we have, which is a 40-foot wall, to get a percent of full height sheathing on that segmented shear wall, 43%. So we're back to the wood frame construction manual. We're going to have to interpolate between 30 and 40. But I want to make sure you understand the header here for this column. It's the percent full height sheathing on the segmented shear wall that you've calculated. Okay, it's not the percent based on full height sheathing or anything like that. It's what you calculate. And so between 40 and 50 is where we'll interpolate, and that's between 1.43 and 1.33, and that ends up interpolating to a factor of 1.4. So we're going to increase what we calculated earlier for the segmented method by 40%, and that ends up being 23.8 feet of full height sheathing that's required on that wall. Well, we actually have 24 feet, so we've got enough. We are going to fully sheathe that wall, but we have to do this check to make sure we've got enough full height sheathing. If we didn't have enough full height sheathing here, then we'd have to adjust, we have to go back and adjust this again, but we do have enough full height sheathing to make this work. And so the perforated shear wall in this case actually works without changing the nail spacing, and we're able to move those hold downs out to the corners, so we don't have those 6 hold downs around the window and door openings in the middle of the wall. The wind load analysis is going to be very comparable. Again, in the earlier segmented approach, that required 9.5 feet. Over a 40-foot wall, that's about 24%. We come up here to between 20 and 30. We're going to interpolate between 1.67 and 1.54. It gives us a 1.62 factor. Multiply that, 60% increase over the 9.5 feet, and we end up 15 feet of wall, and that's plenty to work with the 24 feet that we have. So this is our summary table here, W5.7. This is the this shows you what controls between seismic and wind in the analysis that we've just done. And so you see some of the numbers falling out here. This is the segmented approach that required 17 feet. This is the perforated approach. It required 23 feet for seismic. Seismic actually controls on this north wall. But you see the nail spacing is 6 inches on center around the perimeter. So that's pretty typical nail spacing, and that all works. When we get to the first floor, you'll see how we have to back that nail spacing down to get some of those floors to work. So I'm going to speed up a little bit here. We're going to run out of time and make sure that we can get through this. I'm not going to do floor joist lookup tables. We did the rafter and ceiling joist tables last week, so these are very, very straightforward lookup tables. Floor sheathing, very simple lookup tables. I will spend just a second talking about the lateral framing connections. So now we've designed pretty much the framing for the second floor. Now we're going to start looking at some of the connections to make sure we've got our load path, have all of those framing connections tied together. To do that, I'm going to jump to table 3.1, which is a very handy table in the wood frame construction manual on page 145. And this is a nailing schedule similar to what you see in the IBC conventional construction provisions, the IRC provisions. The difference here is that there are some lookup tables that are referenced here that allow you to go quickly to see how you've got to nail the rafter to top plate, for example, that we'll look at here in a second. But for top plate to top plate connections, we can go in here and take a look at the top plate to top plate face nailed, and we see that that's going to require that 2 16-penny commons. We also show the box nail requirements there and how often those need to be spaced. So that's where these numbers are coming from. I won't go through each one of them. You can do that on your own. But as you work down through the wall assembly, and then wall assembly to floor assembly, and then the floor to the wall below, you can just work right down through and make sure, you've got that load path covered. We're going to look a little bit now at the connections, and again, let me take a look at my notes real quick to make sure. Yeah, we do have a pole, but Marcy, I'm going to skip that one because I didn't cover that very well. Let me just tell you what that pole would have. Let me tell you what that pole would have been, and that is that. In the wood frame construction manual, we cover both the perforated shear wall and the segmented shear wall approach. We do not cover force transfer around openings. Force transfer around openings is covered in the wind and seismic standard, and so there are these two approaches, perforated shear walls and segmented shear walls in the wood frame construction manual. So let's look a little bit at some of our uplift, lateral, and shear connections. Again, we'll work through this pretty quickly because we did some of these last week when we were looking at a roof system design and how we connect our roof system. to the walls. Very similar approach here. We'll go to table A-3.4. So get to the list of tables here and the appendix. And so that's on A-3.4, or exposure B. And what this is going to give us are the uplift strap connection requirements. For roof-to-wall and wall-to-wall, which is what we're looking at here, is our wall-to-wall connections between the second and first floor, 160 miles per hour, 16 inches on center, and a roof span of 32 feet. So you see that requires 4 10-penny box nails in the end of each strap. So across each stud, from second floor to first floor, we're going to need 4 nails in the end of each strap if you choose to use straps. Alternatively, what we can do is turn to table 3.4, and I'm going to jump there quickly. And if you're following along in the wood frame construction manual, we are in table 3.4, page 167. Page 167, the wood frame construction manual. Let me blow that up so you can see it a little bit better. And again, we're in exposure B, 160 miles per hour to make sure you're in the right table. And for 16-inch on center rafter and truss spacing or wall spacing, over here under 160, you see that for lateral and shear connections, sorry, that you can pull out. Hang on, I'm sorry, I'm not seeing the. Oh, yeah, the 479. Sorry, the uplift connection is 479 for that 32-foot wall spacing. And so that is your uplift connection. And then for, I'll come back in a second to the lateral and shear connection. So if you need to determine just a load instead of a prescriptive number of nails, you see that this table 3.4 allows you to determine your loads. Now there's a new provision in the wind and seismic standard that's also incorporated into the wood frame construction manual that also allows you to use wood structural panels to resist uplift instead of straps. And so for that, we're going to jump to table 3.4b, and again we're exposure B. And what you do for this table is you take a look at what you calculated earlier for your shear wall design. So for our shear wall design that we calculated earlier, we're going to be somewhere in this set of columns. We've got a 6 and 12 nail spacing, and so that shows up here in column, or in this first row. And so if we were to reduce that nail spacing around the perimeter down to 4 inches and work out here to the 160 mile an hour column, we see that doesn't quite work. We can't really get that to work. We could try to go to 3 inches on center with 1 row of nails. That doesn't really work. So let's take a look at 2 rows of nails at 4 inches on center and work our way across, and we see that that actually works because a 36-foot maximum roof span is possible there. So what we've done with this very, very simple table is we've determined that we can reduce our nail spacing on the perimeter of our wood structural panels to 4 inches on center instead of 6 inches on center. And by doing that, we're going to handle both the lateral shear loads and the uplift loads. And so it does require 2 rows of nails at 4 inches on center, and so that gives you basically a 2-inch nail spacing, but those are staggered. So those are staggered nail spacings There are figures in the wood frame construction manual that show you the detailing requirements, and showing those figure references here at the bottom. But that, again, is another tool in your arsenal, another way to allow you to use wood structural panels instead of straps to resist uplift and shear. And so that's what Table 3.4b is all about. In the workbook now, I'm going to jump down and just take a look quickly at determining our hold down capacities. And so the thing we'll want to do here is jump to Table 317F. So I'm going to go back to the table of contents. Let's get to Table 317. And 317F is on page 223. And on 223, you see a very simple table, and it says that you can use this for both the segmented and perforated shear wall capacity requirements. And you say, well, how's that possible? Because those are two different approaches. Well, we've simplified, again, to provide a simplified approach in the wood frame construction manual. We've developed a simplified procedure where we're assuming that the first panel in the corner of the wall system is going to pick up 100% of its capacity before spreading load out into the rest of the wall. So our hold down capacities then are based on capacity of the shear wall rather than load on the wall. And you think, well, that's really can be conservative, and yeah, that's true, but it also allows a simplified analysis. We certainly would not prohibit an engineer from designing, assuming the actual loads on the wall and spreading those loads out across the length of the wall. It does make it a little bit difficult to offset those hold downs with dead load, and so we're also not offsetting hold downs with dead load because it's hard to determine tributary area for offsetting dead load. There's a lot of engineering judgment assumed in that approach. And so this approach, by assuming 100% capacity in that first panel, gives us a very easy way to tabulate hold down capacities, whether we're talking about the segmented or the perforated method. And so for the wind analysis, you see the values higher because we're counting for gypsum on the interior as part of the shear wall capacity, whereas for seismic, we don't count the gypsum as part of the shear wall capacity. And so those values are going to be different. And back in our table in the workbook on page 45, you see that for seismic, we're calculating an uplift of, or a hold down capacity of 2151. And for wind, it's 3924. So we've got your three stud corner and four stud corner details shown here at the bottom. Again, a very simplified approach, but we're not going to prohibit you from going in and calculating actual hold down capacities based on your engineering judgment. So I'm going to jump from there to look at a couple other sheathing and cladding attachment requirements. So earlier we looked at tables to determine the minimum sheathing thickness for suction. These tables, table 311, I'm not going to go there, actually determine or help you determine your nail spacing requirements for suction. So the nail spacing requirements that we've done for shear walls are 6 and 12. For suction loads, we see that those actually work as well. Next, we're going to look at our header and girder connection tables. And so I'm going to jump to table 3.7. And so we got to make sure that we're connecting all of these headers and girders into the wall system to make sure that they're going to stay put. So I'm in table 3.7. Again, we're in exposure B. and we've got a roof span of 32 feet, so we're going to end up having to interpolate between 24 and 36. But under this 160 mile per hour column, we've got both uplift and shear for our headers tabulated. So we come down here for this 6-foot header span that we're looking at. You actually end up interpolating something less than 1,200 pounds for uplift and something a little less than 500 pounds for lateral. And we see those interpolated here in the workbook, a little over 1,000 pounds for uplift and 500 pounds for lateral. Again, a lot of analysis behind this table, and if you look at the commentary, you can see the analysis that goes into this. So if you are looking to fine-tune that with your own analysis, you can certainly go in and do some of that on your own. The rest of this is looking at the sill plates and other headers that are in the system, and so we won't spend a lot of time there. So here's our summary of the second floor now, and what you're seeing here is that the seismic loads only controlled in a very, very small area, those 2-2 north walls, with the segmented shear wall approach. And so for the rest of the wall systems, the wind loads actually controlled. Those ended up being 2x6 walls because of the lateral, the wind load requirements. So we're using number 3 in stud 2x6s. At 16 inches on center, we've got that 1/2-inch gypsum on the interior. We've got 15/32 wood structural panels on the exterior. I'm showing you both the segmented shear wall and the perforated shear wall requirements there. So for the segmented shear wall, it's again the seismic controlled for this particular wall, but you're going to fully sheathe the perforated shear wall. The hold down requirements are very similar, and then that shear nailing at the bottom of the wall, nailing to the floor system, is 2 16-penny nails per foot from table 1. So it's a pretty interesting comparison there again between seismic and shear. I hope you're seeing, especially out in seismic country, and I know this is a very high wind load, but if you've got wind loads that approach anywhere in your area 160, that can very easily start to control in the design process, because we're designing for a D1 here, and so that's about, that's a fairly substantial seismic analysis as well. And so you can see those comparisons here. We looked on page 49 earlier at those differences. Again, the perforated shear wall is fully sheathed with hold downs at the corners. And the segmented wall, you're only required, a certain number of segments, but you've got 4 or 6 additional hold downs on the interior wall that you can get rid of. So that's the detailing summary there. Page 50 of the workbook, we've got the header detailing summaries for both the raised and the dropped headers. And so you can take a look at those summary sheets as well. If you were just doing seismic, obviously that doesn't affect your lateral header or uplift designs on your header. You could use your gravity-only header designs here at the bottom. All right, so that's the end of the second story, and again, I'm going to get to some of my notes here, make sure we don't have another polling question that I may have skipped, and we're at about a half an hour to go. I'm going to try and finish up here with the bottom story in the next 15 minutes, and we'll be able to skip through much of the second floor analysis, because we've already done similar examples on the first floor. These load-bearing studs, we've determined how to do that in the lookup tables. Again, we're going to end up with 2x6, number 3 studs for the load-bearing walls. We've done the top plate analysis. We've done the header designs. I'll point out here that for this particular header analysis on the first floor, we've now got 2 floors and a roof ceiling assembly above. And so to sort of show you some alternates in the tables, I've designed a 20F glulam header, 3 1/8 by 13 3/4, to work in this particular case. One thing about the assumption for 2 center-bearing floors is if all of your windows line up from second floor down through the first floor, then you've already carried your floors and your roof system above. So you could possibly get by with smaller headers here, but you still need to make sure that you do your jack stud analysis and come up with the correct number of jack studs based on both floor systems, because that's based on bearing. So you think there's a note down here at the bottom. It says if all the first floor headers align with the second floor, you could get by with some smaller headers on that first floor, but you got to make sure you cover your jack stud analysis. So we'll skip then to our shear wall design. Again, most of the rest of this here is very similar to what we've already looked at before. So now I'm on page 57 of the workbook, and what I want to point out here is now we've got a roof, ceiling, and an additional floor above. And for the wind analysis, or I'm sorry, for the seismic analysis that we're looking at here, you see that when we design wall 1-1, because of those aspect ratios, those are 3.5 to 1, or sorry, 2 to 1 aspect ratios, and because we don't quite meet those aspect ratios, we've had to decrease our nail spacing to 4 inches on center to get that to work. And so let me go and show you from table 317D how to use that table to get that other adjustment factor to use those tighter nail spacings. So I'm going to jump very quickly to 317D. So here's where we were before on page 218 of the wood frame construction manual. And remember, I told you to circle down here at the bottom your baseline, which is right here. I'm going to go to the next page. You see that this is a 6-inch on center edge nail spacing. So let's say we're going to decrease that nail spacing to 4 inches on center. So I'm going to go over here to page 219. I'm going to drop down near the bottom of the page and make sure we're in the right spot. We've got 15/32 wood structural panels at 16 inches on center. And I'm going to change the edge nail spacing to 4 inches on center instead of 6. I've got my 1/2-inch gypsum wall board. You see that increases the capacity of our shear wall to 590 for wind and 350 for seismic. So what we then have as adjustment factors will actually decrease the length of wall required because we've increased the capacity. So now back over here to our example, at 4 inches on center, our seismic adjustment factor is 0.68. So we've got some other adjustment factors that we would plug in as well, but we take that 18.1 tabulated value and adjust by each of these, including this adjustment for the 4-inch on center spacing, and now we see that it only requires 13'6" rather than 18 feet that's tabulated. And so that allows us to make those seismic shear walls work. We get to the perforated analysis, and for the perforated shear wall analysis here on page 58, well, now we see we've got red everywhere. The north wall north and south walls don't work for wind or seismic. One of our load-bearing walls now doesn't work for wind, and it's because we're on the first floor. We've got a whole lot more wind and seismic load on this structure, and you can see that those required wall lengths have just increased pretty dramatically from the those tabulated values above. But there's a way, because we're still at pretty much 6 inches on center spacing for all those walls. There's a way to go back, and this next page 59 is an analysis where we're going to go back and we're going to drop the spacing for those walls down to 3 inches on center. And because we do that, we've got a new adjustment factor that basically cuts our wall length requirement in half. So that makes sense, really. You go from a 6-inch on center nail spacing around the perimeter to a 3-inch on center nail spacing, and you're going to expect to pretty much double the capacity and cut in half your wall length requirement. And when we do that, our segmented length is now about 10 feet, and our perforated length, based on our perforated shear wall adjustment factor, is going to bump us back up to about 20, not quite 25 feet, and that works based on the length of full height shear wall that we've got in this wall. We've got 25 feet, so we come in just under on that bottom wall. Now we still haven't gotten this wall down here. This is the one wall 1-1. We can't get that to work for our perforated shear wall for wind, and I'm kind of stubborn. I really want that wall to work. We're just outside of making that work. So for you engineers in the audience, if you want to go to the special design provisions for wind and seismic, and I'm gonna jump down here and show you that analysis. On page 61, since we couldn't get that to work with that perforated shear wall approach in the wood frame construction manual, I'm going to go to the wind and seismic standard. And what the wind and seismic standard gives me is, instead of a table, and let me jump to the table here in the wood frame construction manual, instead of this table 317E, I've got an equation in the wind and seismic standard. And can't remember the equation number. It's probably here in the notes somewhere. But that equation allows you to calculate the actual percent of sheathing in that wall by subtracting out the window and door openings. What this table in the wood frame construction manual does over here in 317E is it assumes a maximum unrestrained opening height. So it's going to assume that if you've got a 6-foot opening, that's going to be present at all of your openings. This equation in this wind and seismic standard actually allows you to calculate your exact full height, your exact openings, and so that allows you to sharpen your pencil, and you see that that wall now works, even though it's pretty tight nail spacing. And again, the summary table down here at the bottom shows that for our perforated approach, it's going to require 3-inch on center spacing for seismic, 4-inch on center spacing for wind, but we've got all those hold downs out to the corners, and so that's good news. That's really helpful for us. I'm going to catch up real quick here with my notes, make sure that and Marcy, again, for your benefit, I know we're running behind, so I'm going to skip the whole questions
No problem.
up to this point, and we'll get through to some of the other information that we want to cover here. So let's jump on down to our lateral shear and uplift connections on page 64 of your workbook. So we'll skip past the floor framing, we'll skip past the table 1 lateral and framing connections. Here's something new that we haven't seen yet. And again, these little icons up here in the top are going to show you that we're looking at the connections of the first floor to the foundation system. So this is the wall assembly to foundation system. And we're assuming a crawl space or a basement here with this particular design example. Now we won't design in the wood frame construction manual. We don't design that basement system. That's concrete or masonry. We're wood folks, so we don't have the foundation system design. But we are going to show you in this example how to connect that wood wall system to a foundation similar to what you're seeing above. And again, we're going to be looking at uplift, and lateral, and shear loads. And so we'll jump to table 3.2a to look at, let's see, hang on, let me go in order here. So we'll jump to table 3.3a4, and again we're getting closer to the front of the book rather than the end because we're kind of working our way back through the load path. So 3.3a4, and because we've got 5/8 inch anchor bolts, we've got a ground snow load of 30 pounds per square foot. We're in seismic design category D1. We've got that 1.25 length to width building. We've got a roof ceiling and 2 floors, so we're going to be somewhere here. Let me expand this table a little bit. And building dimension of 32 feet, so we're going to be somewhere between 3 and 5, and so that interpolates well to 4. So for this particular example, our seismic shear number of bolts required along that wall is along the 40-foot wall, I believe, is 4. And so there are some additional adjustment factors that we would look at in the footnotes, but that bolt spacing then ends up being 114 inches. Pretty sure that's not going to control. So then let's look at our shear loads from wind, and that takes us to table 3.2a. So over in the wood frame construction manual on 3.2a, make sure we're in exposure B, 160 miles per hour, and again we're looking at 5/8 inch anchor bolts here. So a roof and 2 floors, working our way across to the 160. Shows that 9 bolts are required. And again, footnotes with those tables could be used, and then you calculate a 57-inch spacing. Well, so that's we've looked at our shear loads for wind, we've looked at our shear loads for seismic. Let's look at our wind uplift loads, and that's in table 3.2c. Pretty easy uplift table here for exposure B, and this one's actually shown in maximum spacing for 160, and we'll look at the worst case, which are the interior zones. I'm sorry, the worst case are the 8-foot end zones of 31 inches, and that's what ends up controlling our design. So uplift ends up controlling the design for those shear anchor bolt spacing, 5/8 inch anchor bolts. Let me tell you what's in this particular table here in the workbook, page 65. When we've done an exercise like this before, where we can look up our actual loads, and so if we were to go to table 3.3, we could look up our seismic shear loads instead of the spacing. and use some adjustments to come up with a seismic shear load of 198 pounds per linear foot. We can look up our wind uplift load of 218 pounds per linear foot, and our shear loads of 421 pounds per linear foot. Want to just make mention of this row here that doesn't show a lateral load calculated for this basement or this system. And so this footnote at the bottom is the reason for that. The lateral loads, since those might include soil loads, are not shown here. So we could calculate lateral loads, but you're probably going to have to do a soils analysis to design that basement system anyway, and so we don't show those lateral loads in this particular one. You could use uplift straps instead of instead of just calculating your loads, and again, table A34 allows you to calculate those uplift straps. We've looked at that already. And again, you could then, using table 3.4b, use wood structural panels to resist both uplift and shear loads instead of straps. I'll point out here that this one particular wall doesn't work in that case. There just isn't enough. We've already got our nails at a pretty tight spacing, I think of 4 inches on center, and there just wasn't enough capacity to get those to handle both lateral shear loads and uplift through the wood structural panels. So what you could do is go to the segmented shear method, which will allow you to do that, but the perforated method will not allow you to do that. The other note here that's highlighted at the bottom is that when you do design these panels for combined uplift and shear, your anchor bolts need to have 3 by 3 inch steel plate washers at 16 inches on center, because with that additional uplift in that sill plate, you're putting cross grain bending stresses on that sill plate, and so what we found was that would split out around a normal size anchor bolt with a washer, and so that's why these 3 inch by 3 inch plate washers are required. An additional note there is that in the 2015 wood frame construction manual, we're in the 2012 version, but in the 2015 there's a new table that allows you to go beyond this 16 inch on center spacing to something a little more reasonable for certain uplift loads as well. So that's something to be aware of. Page 68 of the workbook. The thing I want to point out to you here is that the hold downs now are cumulative down through the structure. So we're going to take our second floor hold downs that we calculated earlier, which was 2,151 pounds for that second floor. We're going to add that to the first floor hold down requirements that we calculated to come up with our new hold down requirements of 6,200 pounds for seismic. What ends up controlling in this particular example is wind across the board, and you see our hold downs are close to 10,000 pounds for the perforated shear wall approach at those corners. Now, the other note here is that if you've got those hold downs at the corners connected properly for shear, you don't have to use hold downs in both directions to handle both walls. You can take whichever one controls. If it's your load-bearing wall that controls, then you can use the larger of the two at those corners as the control. And for this particular example, looks like this wall 1-1 is the biggest one. So as long as you've got 10,500 pound hold downs at all your corners, you're good in both directions. All right, so Michelle, we're getting pretty close to the end here. I'll probably do a summary and then we'll take some more questions. So down to page 71 shows a wall detailing summary. Again, We see the difference between the segmented and the perforated shear wall as far as the edge nailing requirements. Wind controls every wall in this particular example. We're seeing our hold down requirements there at the base of the wall. Our anchor bolt spacing, if we decide to use the wood structural panels in combined uplift and shear, we're seeing our anchor bolts need to be at 16 inches on center. Our shear nailing for our shear walls to the floor system needs 4 16-penny nails now instead of 2 that we got for our second floor. So it stands to reason that when you get down to that first floor, you've got additional loads, that you're going to have higher shear requirements shown. And then this shows you the difference in that segmented versus perforated approach. Very dramatic here for wall 1-1, where the perforated shear wall has 2 hold downs, 1 at each end, and that gets rid of how many? 2, 4, 6, 8, 10 hold downs in the interior of your wall system just by beefing up that wall, making it a little stiffer. So let's stop there. Michelle, I'm going to ask you to come back, and we'll see if we've got a few questions here that we can answer in the last 10 minutes.
And we do. We have a very inquisitive crowd.
I bet.
So here's one related to nails, and please address the nail size and corrosion resistance related to, I guess, galvanized nails and how that relates to the size of the nails. And if you could expand also on guns, using nails and guns.
Okay, yeah, okay. So I'll work backwards with that. We get a lot of questions about pneumatic or power actuated or power driven fasteners. There is a website by the International Staple and Nail Tool Association, ISANTA, I think, isanta.org, and maybe Brian or someone can put that link there if we can verify that's the correct link. On their website, they have an evaluation report through ICBO, I believe, ICBO, through ICC. That's pretty funny coming from an East Coast guy, isn't it? Through ICC for power-driven fasteners, and they would give the equivalents to the common and box nails that we tabulate in all of our documents. So as long as you've got comparable diameters, nail diameters, and any length requirements that might be needed for shear walls, for example, then those power-driven fasteners can be used. To address the corrosion issue, you really have to look at the manufacturer's literature. So especially in sill plates that are going to use different preservative treatments, then the fastener manufacturers have galvanizing or other requirements for those fasteners that are going into pressure-treated, preservative-treated wood. For the anchor bolts, I think there is an exception in the code specifically for half-inch or greater anchor bolts, but I don't know that any exception like that exists for wood structural panels, and so that's a real issue that if you're driving nails in your shear walls into treated wood, into sill plates, then you need to make sure you're using the appropriate fasteners for that.
All right, good. Another question came in and said, will you be updating the guide for 100 mile per hour exposure B?
Oh, that's a great question, and I need to go take folks to the commentary, and let me get there real quick, because the wind load provisions have kind of gotten things messed up a little bit. So let me get to this part of the commentary so we can talk a little bit about wind loads. And if you're with us the first time, you've seen this table, but table C 1.2, and this table's in the IRC. I can't remember if it's in the IBC, but unfortunately what happened in the IRC is that they incorporated maps for the ASCE 705 basic wind speeds, And the 2012 codes are all based on ASCE 710 wind speed. So this is the table that maps those out. And so when I showed the 115 mile per hour table, I'm showing ASCE 710, which is equivalent to the 90 mile per hour table in ASCE 705. So look carefully at these equivalency maps, because the new maps are based on a 700-year return interval. The old maps are based on 50. It is causing some confusion, but these conversion tables will help you in making that conversion. So I'll take that question though, Michelle, and we'll say that we are creating some additional guides above 160 miles per hour. I think we're going to do up to 170, maybe 180. You can see in our tables we go up as high as 195 in the wood frame construction manual, which is equivalent to the old 150. And so we're going to tabulate 170 and 180 high wind guides for exposure C. Our understanding is exposure C is required once you get up to those higher wind speeds.
Okay. And looks like there's some commentary on that too. Do you have any more time for one more question? Okay.
Yeah, we've got time for a couple more actually.
Okay. So the wood frame construction manual does not cover force transfer around opening shear walls. You need to go to the wind and seismic provisions. Mm-hmm. But there was a question related to perforated shear walls and whether or not strapping is required around the opening.
No, and that's really that strapping is really part of the force transfer around openings method. So if a designer is using that approach, then they may require straps around those openings.
Right.
But the perforated shear wall approach just requires that the entire wall be sheathed around above and below window and door openings, but strapping is not required.
Oops. Okay, and here's another question related to the wood frames construction manual and connecting to, I think it meant, the person meant timber piles and wood girders. Is there any connections or method of analysis in the wood frame construction manual?
What I'm going to do for that question is go to our website and go to our education page. And I'm going to scroll down here to our different categories on our education page for the AWC standards. And there is a 4-part series that you see right here, beginning with STD 310, 311, 312, and 313. All of these were done a couple of years ago by Bill Colburn, a consultant, and he pretty specifically addressed, especially in Part 4 here, STD 313, foundation designed to resist flood loads and wind loads on pile-type structures. And so I think that'd be a really good. It's not easy to answer that question quickly, but this resource, this recorded webinar, will allow you to get some more CEUs and answer that question in a lot of detail. So that one's there to take a look at.
Okay. Yeah. We have 2 more minutes. Does Marcy need to wrap up, I think?
Okay, Marcy, if you want to come on back and take us through the close of our session. I'm going to thank everyone for participating today. I appreciate the questions. Again, I know we cover a lot of information in a pretty short amount of time, but we are, just to let you know, going to be updating to the 2015 version of this workbook, and based on the comments and feedback that we've gotten from this sort of new series, this is kind of new to us too. What we do plan for next year, I think, is to break this up into smaller segments and provide some more webinars that maybe just focus on certain parts of the wood frame construction manual and the workbook, rather than covering as much territory as we do in 2 sessions. So hopefully this is giving you a pretty good overview of the manual and the workbook, and then next year we'll dig in a little deeper to some of the provisions that we've covered here in these last 2 sessions.